We're very casual. Okay, so wait till that goes, and here we are. Okay, welcome everyone. This is the Project Guts MOOC for 2017. We are having a webinar to introduce week 3. Basically, we wanted to give you a tour of the models and introduce you to our fabulous Project Guts facilitators. So on the phone, we have Miriam Niebla, and she is from Broward County, Florida. You want to say hi, Miriam?
Hello. I'm excited for you guys to see this.
Great. And then we have Stephen Boyd, also from Broward. Did Stephen fall off? Maybe. Josh?
I did not fall off.
Oh, I'm sorry. I just can't see you anymore.
No?
No.
You have to scroll up and down.
Oh, I have to scroll up and down. I'm sorry. Stephen. Yeah, excellent. And then we have Josh Bierman from Virginia.
Hello.
And Lena Gurman. And Lena is from Santa Fe, New Mexico.
Yep.
And
Hi.
finally, Cheryl Areola couldn't be with us this evening, but she is also from Broward. So just an overview, we are offering support for 4 modules. Module, I think it's called 2A, Greenhouse Gases, and Stephen Boyd will be the facilitator for that module. Then we have module 2B, Water Resources, and Miriam Niebla will be facilitating that module. Ecosystems Dynamics is with Cheryl Areola, module 3. Module 4 is Chemical Reactions with Lena Gurman, and also Josh Bierman. And Josh has worked up some introductory chemistry models as well. So we were just gonna hand over control to the facilitators, and if you're able to, you can grab the screen now, and we'll start with Stephen.
All right, give me a moment here.
Sure.
So you want us to open up Starlogo Nova project on our screen and then share it, right?
Right.
Okay.
Yeah. That'll be fine.
Let me see if I can get that.
All right, did that work?
Yes.
Cool. Basically, this is the greenhouse gases module. And it starts off with a simple model that's already set up. And in that model, the first thing you do is, of course, ask the students to observe what occurs. When we hit setup, the sun appears. And when we hit forever, we start to see what's ostensibly solar radiation. And we've got a graph that's illustrating what's happening to the temperature over time. Now, some of the solar radiation is absorbed, and some of the solar radiation is reflected. And so that makes a difference in what happens to the temperature. So we've got multiple breeds here. You'll notice turtle's no longer there, which has been renamed. In the world, it basically sets up the graph. It sets up the sun. It sets the data for heat to count the heat. You can see here, count heat within 200 steps. So they basically ask the student to watch the model, ask them what happens. We're introducing the concept of the surface of the planet, what they call it, albedo.
Mm-hmm.
So we later develop an albedo slider because in the original model, we've hardwired it to I think it's at 60% or something. So we change it, we add a slider. Sorry, I'm putting that in 3D view. On the Macintosh, it's the Option key. I think it's Control key on the PC and the mouse. And again, it sets up. And then forever, what happens then is now the student can begin to run experiments, because they can look at, well, if albedo is 0, what happens to temperature? And you can see it skyrocketing. And if it's at the opposite, it'll crash. You'll see it go down to 0. So they can start to run experiments, getting the experimental design form. I know students have a hard time defining independent variable, dependent variable, but it gives you an opportunity to run through that when they design their experiment, and how many trials are you going to do, and so forth. And then this particular model, I like it because you just keep adding extensions. You have the ability to just keep expanding the model. The culmination of this one is that you provide a source of CO2. In this case, it's a factory. It could be cars. It could be any number of things that can make the CO2. It could be dinosaurs. And you can see it's gotten quite complex. Because here we hit setup, of course, we get the sun, but it also, in this case, built a factory. That factory will give off CO2 when you run the factory. The CO2 can rise. We have it rise just halfway up, and it does wiggle walk to kind of expand that into a cloud. And when the heat rises, it can be reflected by that and go back down to the bottom, which in turn raises the temperature. So they get to study, and you can see here now someone's added how much CO2 is emitted from the factory every tick. There's an automated time run, so you can begin to include even more variables to make it more realistic. And that's basically what this model does.
Thank you, Stephen.
Mm-hmm.
So I guess we'll go to the next model, and that is with Miriam. And if you could stop sharing screen.
I'm looking for it.
Okay. I think it's up at the top.
There it is.
Okay.
Perfect.
Great. Thank you. And now I have to figure out how to grab screen again.
You grabbed it.
Darn technology.
Yeah.
Just a warning, I'm flying blind here.
You're what? You're flying blind? Yes. I'm having problems. Okay, I'm going to exit full screen view and move you guys to the side.
We can see you now, Irene.
Yeah, but it doesn't come up and show me the grab screen, share screen option. Maybe it's up on the top. Start share. Okay, there we go. Okay, now we'll move on to the water pump. And Miriam, I have loaded the base model of the water pump, and I'm going to hit the setup button. And talk me through, and I'll click buttons as you direct me.
I will do my best here. So what happens is with the water resources, it basically runs through the idea that water, or the water cycle, as things get shared out, there's no renewable resource here. You know, there's a finite amount of water, and it's a question of how we actually distribute it and how we actually use it. So the very top part of the module, like once you press setup, there is a single pump. It is red with a small yellow bottom. And as you press forever, water begins to fall down in the form of rain, and it begins to percolate through the ground. And as it hits the yellow part of the pump, it actually goes back up into the atmosphere, if you will, and then it starts kind of the cycle all over again. You can, as part of this module, one of the first things that it asks you to do is to kind of create a second pump. Well, what happens now if you have two water pumps? Is there enough water for it to go to the different pumps, etc.? So that's the first thing that it asks you to do. A little mini tip, if you will, when you make the second pump, you may want to change the very bottom color of the pump. And the terrain color sometimes is a little glitchy in the sense where it likes white, yellow, red, blue, and basically any primary color. If you try to use a magenta or a green or something else as part of the water pump, for some reason it just doesn't always register. So just letting you know as an FYI when you're going through your code and you're actually creating this. Then you get into the manipulation of the model, if you will. When you go into the manipulation of the model, it's basically asking, well, how can you tell what water is going through each pump? And it asks you to actually add an evaporation slider. What happens as things heat up? Is the water actually reaching the ground? Eventually, you kind of run out of water, if you will, if you have either too many pumps. One of the different experiments that you can run is, well, how many pumps can you run and still have a sustainable system? You do have a little bit of control over the initial amount of water that you can actually change using a slider as well. And eventually it gets to the point where you can run some pretty, top-notch experiments when it comes to, you can actually change the different layers of grounds. Well, what happens if there's a street there and asphalt? How does the water continue to fall and go around through the ground? You can actually run experiments of what happens if you have too many pumps in a specific area. What happens if you, and the experiments go on and on and on and on. Did I explain that well? I'm sorry, I'm flying blind.
Yes. No, that was great, Miriam. So what I've done is I've brought up another model that, that's great. That has two pumps in it, and I just set it up and I changed the evaporation rate to 43.8%, and I'm hitting forever. And now we can see what happens with two pumps and evaporation.
Right.
And can add both data boxes for the pump, the yellow pump versus the white pump.
The
amount of water. Excuse me?
Usually I challenge them to make it, so how do you tell how much water is running through pump 1 versus how much water is running through pump 2? And that usually adds a little extra element of, okay, well, how do you distinguish it? And then how do you make a data box so that you can figure out how much water is running through each pump?
Right.
Depending on the kind of experiment that they're running.
Thank you, Miriam.
There's also a nice complex adaptive system in this one where it forms a cone of depression around the wells. And in earth science anyway, we talk about the cone of depression that happens around wells, and it's not coded anywhere in the model. It just turns out that way, where it makes this cone shape.
Yes. Lena, you had a question?
Yeah, I'm noticing like some of the water drops have different sizes. Is it just something?
Yes.
Why is that? Is it?
That's the evaporation rate is set.
Oh, as they're coming in?
Yes. Yes.
Right. So some evaporate, so by the time they drop down, they're rather small.
Okay.
And some never make it at all.
Right.
Okay.
So that's another thing that another variable students can experiment with. Okay, thank you, Miriam, and good to see you.
Oh, am I actually visible now?
Yeah, yes. So the next model to talk about, and this is the one Cheryl Areola will be facilitating, is the ecosystems dynamics model. And in this one, when you hit setup, your world is populated. Let's see if I can show it better to you. With rabbits, they look like rabbits or chipmunks, I'm not sure, and grass. And one of the early challenges you could give your students is to try to find a way to balance the ecosystem. And let's see, the graph shows the population size over time. Oops. And you can see that when rabbits eat grass, they might gain enough energy to reproduce. And the grass too is reproducing. So all looks okay at this point, but lo and behold, what do you think is going to happen?
Either we're going to run out of grass or, oh, well, first rabbits are multiplying.
Lots of rabbits. So you can challenge the students to figure out what the different possible outcomes are. And there are really three somewhat just end scenarios.
Either all the rabbits will take over and then die because there's no food, or the food will take over but the rabbits will die, or there's some kind of balance system, ecosystem.
Right.
I'm assuming the grass is multiplying too there, but I'm not sure in the base model.
It is. Yeah, will they find it in time or will they starve? So we don't have, at this point, the rabbits are not hunting for grass. They don't have a cone of vision or anything.
They found it.
Maybe.
One tiny, there's one tiny.
We'll see what happens. I'll mention there's a speed slider over in the right-hand corner, and down is like putting your foot on the gas and speeds up the simulation.
The grass multiplying, but I don't know.
It multiplies very close to itself, so the clump just gets denser. I think we're having a extinction event very soon here. Okay, so you'll see, kids are very interested in this model, and they can change the thresholds that are necessary for reproduction of rabbits. They can change the rate at which grass grows. And one final challenge that's a lot of fun is to have add a top predator. And with that predator, you could have them predict whether they think that'll make the system die out even faster, or perhaps things remain the same, or perhaps the ecosystem can persist longer with the top predator. And that's a fun experiment to run. Okay, any questions about this one?
I have a comment. I remember that this model, when you add a predator and then you supposedly can copy all the movements from the rabbit page to the predator page, there's a lot of changes that need to be done, and it can break the model fast if you don't remember to change every trait to be the trait.
Right, you have to rename.
We have to rename a lot. So I usually recommend that they copy one block at a time, one section at a time, and make sure they have that working before people are usually tempted to copy the whole page from the rabbit.
Right. Uh-huh.
Yeah.
Okay. Lena, are you ready to grab the screen?
Sure, let's see.
Okay.
I will share screen, and then I have to find, here it is. Can you see it?
No, we see you. Oh.
How do I, okay.
Look at,
Do I have to close
in
this?
the menu bar where it says meeting.
I
Up
lost
at the top,
Okay, I
menu
have
bar,
menu
it
bar.
says zoom.us. And then next to that, it says meeting.
Yeah.
And then down below, it
Start.
says start share under the
Okay.
meeting menu.
Okay. Let's try that. Okay. Now, do you see it? But there's a block, there's a window in front of it. Desktop 1. I'm seeing something called desktop 1.
So it also looks like the keystroke is,
You don't see my screen?
no.
Huh. Share screen.
Oh, there we did. Yep,
Okay.
now we do.
Okay.
You got it.
Wow. Okay. I don't know how I got here, but I got it.
Okay, good.
Okay, so for this chemical reaction model, you know, people sometimes when they first look at it, they think it's complicated, but it's really not. It's not supposed to be. It can be done in a very basic chemistry class. It doesn't have to be for honors chemistry or AP chemistry. The way I usually talk about it is that the reaction is the reaction of copper solid with silver nitrate. And any chemistry teacher usually have the copper tube or copper wire in their class, and they can order a silver nitrate and they can demonstrate that experiment in class or Google it. There are plenty of videos. They just Google copper plus silver nitrate, and there's plenty of videos. So it's always good to start with a video to really see what the actual reaction looks like. Then the next step is to look at the model, and if the teacher does not want to talk about the chemical formula of each compound and element, there's no need to talk about it. There's no need to talk about copper is Cu and silver nitrate is AgNO3. So it can stay at the level of just words if they don't want to really work on formulas. They don't even have to talk about balancing equations. This can be very basic in terms of what is a chemical reaction, the chemical reaction involving two reactants, and there are going to be products. What are the signs of a chemical reaction? And we start here with the setup. And the other important piece about a chemical reaction is that water is important for the reaction to take place. You dip a copper to wire in a solid silver nitrate, nothing's going to happen. And so I think as a chemist, it's important to emphasize the point of how important water is in breaking down the ionic reaction and the positive and the negative ions. But again, no need to talk about it if the teacher doesn't feel comfortable. But that's why in the setup we start with water molecules. Then we add the copper strip, and then the program adds 150 copper atoms. Again, no need to talk about moles. It's just atoms. And then the amount of silver nitrate is a variable. And once you add the silver nitrate, and you click forever, what's happening is now the silver nitrate is aqueous. So it's in solution, it's moving. And when it collides with the copper, it will convert the copper to copper ions, and silver starts forming instead. You see on the right-hand side, we've got the silver atoms that are depositing. And the first thing I usually ask the students is to just start noticing what's going on here. The number of copper atoms, they start noticing that the number of copper ions is going down, the number of silver atoms are going up, silver nitrate is going down. And at some point, they will notice, as you probably will, is that, and we can speed it up, is that by the time the copper atoms go to 0, then the reaction is going to stop. And we will not have any more silver atoms. So, you know, this discussion is really about a chemical reaction. The signs of a chemical reaction is there's a change in color. You know, the copper is now becoming gray in color, which is actually not copper anymore. It's silver. There is the number of the copper atoms when they go to 0, then the reaction will stop. And that means one of the reactants is already all used up. and so on. So here's 0, and then, you know, at that step or at a later step, you can discuss, okay, well, you know, we started with 150 copper atoms. Now we got 300 silver atoms. So start making a table, and then, you know, and, you know, just kind of start saying, well, what do you notice, you know, that the number of silver atoms have doubled. So the reaction, there's some kind of, you know, start talking about balancing of equations, you know. Every 1 copper atom is giving you 2 silver atoms. And then you can stop the reaction, start again, lower the amount of silver nitrate, and start the setup again with a new fresh copper strip and so on, and add silver nitrate and start the reaction again. And then students can make a table and of the amounts they're changing and how much silver they're getting. And hopefully at one point, the discussion about one of the reactants is in excess, what's the limiting agent, when does the reaction stop, and they can see the ratio of silver nitrate to silver atoms is 1:1, but copper to silver atoms is 1:2. So that's the beginning of the base model. And I think it covers a lot of topics in chemistry already. Now the next topic is, okay, well, the law of conservation of mass says, okay, well, you know, what happened to the copper? There's no way that, you know, the copper disappeared. It has to go somewhere. And that's where you go from the base model to saying, well, we need to create a new breed, which is the copper nitrate. So again, by writing the equation, even in words, by saying copper plus silver nitrate is giving you silver plus, what do you think? Well, it's plus copper. Just take the words, copper nitrate, you know, switch partners. And then you need to add that breed. And that's the next lesson, I think, in that module. You add another breed, which is the copper nitrate. It's aqueous, so it will have the same behavior as the silver nitrate in terms of a random walk. And you go from there. You can then, you know, I think lesson 3 or lesson 4 is, okay, well, you know, if you watch the video, the solution actually slowly turns into blue. And so you can then add more breeds where the copper nitrate is not getting hydrated when it collides with water. And it gets darker and darker blue. There's 2 ways to do that. You can do an if-else statement, or you can just create a new breed for every H. Copper nitrate will collide with 1, 2, and 3 water molecules. I don't know if we want to talk about the whole thing, or this is just about the base model. And do you want me to talk more, or this is good enough? Irene?
She just came back.
Oh,
Hi.
so I mean, so I think I discussed the base model and a little bit extra.
Great.
You know, there is a one section in that code about the copper and its relationship with changing color from gray to this section here, where the copper becomes, when it collides with silver nitrate, it turns gray, and then it turns, and then the second step is it. This is the base model. Okay, so wait a minute. There's a place here where I don't want people to worry about, which is this part here. How does the copper atoms get counted? You know, the students doesn't have to worry about this. What this is doing is accounting for this copper plus 1 that forms first before it becomes copper plus 2 and goes into solution. So there is and I can't see it from here, but there's a 2, a half, that is accounted for in counting. That, you know, this is one piece of code that it's not necessary that students need to know about it, but it's all explained in the info box. If you keep scrolling down, it talks about it in 2 different ways, explaining what that divided by 2 means. Okay?
Thank you. Thank you, Lena.
Welcome.
Okay, so if you want to
How do I?
stop sharing.
Okay.
Yep. And then Josh, if you want to show those two introductory chemistry.
Yeah,
modules.
sure. Can you see?
Yes.
Okay. So I was been talking with Irene a bit about how, for middle school science anyway, that chemistry module is a bit more chemistry than what they really need. They get kind of baby chemistry in middle school, so a couple of the things that appear a lot throughout the middle school in Virginia anyway. Curriculum are diffusion and osmosis, and they appear both in the physical science, but also in the life science when you talk about cell transport, and then even in earth science a bit when you can kind of equate it to convection currents. So I created a little diffusion, pretty simple diffusion thing, and then Irene created a different one. So this is the one that I've been working with right here, and it just creates 100 agents all in one corner, and then sets them off on different headings. And then when I hit forever, they start to wiggle walk. And as they move into the different quadrants, they change colors. And the reason I did this was just so that I could have a convenient way to count them, essentially. And you can see it's graphing their dispersion. And I have it sped up, so they're moving pretty quickly, but you could change their speed, you could change the amount of them, you could change how they move a little bit. And the idea is that it will achieve some sort of equilibrium where it won't flatline, but they'll kind of hover around a certain amount where they're all evenly dispersed throughout the entire model. And this one's pretty complete, but one nice thing about diffusion, I'll show you Irene's as well. Here is hers, and she got them counting in a much more, I think, nuanced way, where each agent is counting the amount of neighbors it has within a certain radius. And as they disperse more, that the amount of neighbors within their radius gets smaller and smaller until it reaches some sort of baseline level. But the principle is the same, is that as they get evenly dispersed, it will kind of start to hover around a certain number. And in either case, I think, I'm just knowing my students anyway, I think that this is a little, I think they have an easier time kind of picturing the way that it counts in quadrants than having them count neighbors. But either way, I think the principle is much the same. And the nice thing about diffusion especially is you students could pretty much, as long as they know how to do the wiggle walk command, much of this they could pretty much code all on their own. And so you could ask your students, okay, so how do we create agents and put them in one corner? Okay, now that we've got them in one corner, how do we get them all going in different directions? And then how do we get them moving the way that particles move? Do particles move in a straight line? Do they, et cetera, et cetera. And this is all sort of fresh, but one thing I was thinking about adding would be a temperature slider, which basically controls their speed. And so you can have them move fast or move more slowly.
Mm-hmm.
And then there is an osmosis model that I made. I couldn't find one easily on SL. The first thing I usually do is just see what else someone else has made first. So I made this one. So it creates a membrane, and you can change the pore size of the membrane. And then it has amount of, I said salt, but really it could be any solute. And so then you say go, and they'll bounce off the membrane, but then they'll move through the pores. And as they move through the pores, they change color. Again, just a convenient way to count them, and you can see it's graphing them. This is also on, I'm using the, I was playing with the new SL Nova on this, so if it looks a little differently to you, that's why. And eventually, they'll even out, and when they do, the whole model will stop. So with this one, there's a lot of extensions I thought of. that kids could do. One is the base model probably wouldn't include the sliders for pore size or amount. It would just have a set amount, but of course it's good to get kids practicing making sliders. And then additionally, I was thinking that you could actually include water in this, since it's important. It's an important lesson for students to understand that osmosis is actually water moving and not particles moving. So there could be some account of the ratio of solvent to solute as opposed to just account of the amount going back and forth.
Mm-hmm.
And those are those two. There's one more that Chad made that I thought I would just show as a simple, as one of the more kind of simple chemistry ideas, and that's radioactive decay. And this is also applicable to earth science as well, because when we talk about radioactive dating. So he made this, and again, you can change the amount of molecules, you can change their half-life, and when you set them, oh, this isn't already dead. When you set them off, they start to go. And then when the half-life happens, they, half of them will decay, essentially. Not quite half, it's not always half, but it's close to half, and you can see it makes a count. And this one's more, I think, of a demonstration than it is an experiment, although you could have your students run experiments on just how long it actually takes for those final ones to decay. More than anything, you have a nice decay curve that is also being graphed, so students can see. One concept that students often have trouble with is the idea of a half-life. Okay, well, after the first half-life, 50% is gone, so then after the second life, that means they're all gone, right? No, it's half of half, and then half of that, and then half of that. So you can really see this graphed nicely on his graph there. So that's those three concepts.
Thank you for sharing those with us, Josh.
No problem. And I'm working on an actual module, so they'll be stepped out for diffusion and osmosis anyway.
Great.
There's another simple model for the evaporation of sodium chloride too.
Do you remember where that? Yeah, there was one that was started in Chicago.
I did. But it's under.
You did one?
It's under Star Logo Nova /guts, and you go down the chemistry modules.
Oh, okay.
It's right up to that.
Cool.
I'll check it out.
Well, thank you, everyone. I hope that with all the glitches, we got a decent recording. I might need to edit it to take out the times when we had technical issues, but thank you.
Thank you, Irene.
This will be helpful for a lot of the students.
Technical issues, that's part of the charm.
Take care, everyone. Have a good evening.
Yeah.
It is.
Look at that. Right on time.
Good to see your faces.
Good to see you too.
Take care.
Okay.
All right.
Bye-bye.